Okay, so now let's look at the elastic properties of solids. When we talk about the deformation of solids, we can talk about different types of deformation. One of those is how the deformation is applied, and that's in the stress. This is just going to be the force per unit area. Force per area. So stress then is just equal to force over area. That's going to be in newtons per square meter. This is similar to pressure, or the same units as pressure anyway, but it's not the same as pressure. But well, it's similar, but it's the force per unit area, and we'll see how that comes up in some of the problems. Now, strain then is a measure of the deformation of the solid. There are several different measures of strain. We'll just look at the one-dimensional measure for strain. And then these two are directly related. They're directly proportional. That is that the stress, if you give it more stress, then it's going to increase the strain by the same amount. So if I increase the stress, the force per unit area, by a factor of 2, that will increase the strain by a factor of 2 as well. These are related by the elastic modulus. So the stress then is going to equal this modulus. It's just a constant basically, times the strain. So the modulus is an experimentally determined constant that describes this relationship between stress and strain. We're just going to look at one stress and strain, and that is the elasticity or the deformation in length. You can also find this in area, the deformation in area or the elasticity in area, and then also in volume. And they work out very similarly, but we'll just look at it in terms of length. That is, if I apply a stress to an object along its length, a force per unit area, what is the deformation of the solid? So remember this force per unit area, this is my stress, and this amount that it's deforming the solid, this is my strain. It's deforming, it's actually stretching this material. So I have an equation to describe this. It is that the stress, which is F over A, is equal to the strain. The strain is delta L over L naught. And these are related by something called the Young's modulus, which is just Y. So F is the force applied. L naught is the initial length of the material. A is the material's cross-sectional area. Shown here is the area of this face. So if you had a rectangular prism like this, it would be the area of that square. If it were a cylindrical object like a rope, it would be the cross-sectional area of the circle. Right? And then delta L is the change in length of the material. And then Young's modulus, as I said, is determined experimentally, and it has units of newtons per square meter. You can see how the units work out here because I have newtons per square meter equals the Young's modulus. Here I have meters over meters. Those cancel out. So Young's modulus has to be in newtons per square meter. This is a table with various Young's moduli. As I said, these are things that are determined experimentally. So they would, for example, put a length of steel, apply a certain force per unit area, and then measure how much it increases in length for that given stress. You can try this quick test. This is just a simple problem applying the Young's modulus, remembering, of course, that my force per unit area is equal to the Young's modulus times delta L over L naught. And I give you the Young's modulus. You're just trying to figure out how much this material stretches. This is important when you're building things because you have to consider how much something is going to change shape when you apply a stress to it. And we'll pick up with this in the next one.